OK，谢谢，如忘记了，谢谢。OK， 11:10的第3堂课。当这门课没有外国学生的时候，我们就可以多讲一些中文了。但有外国学生 ，OK， OK， OK， all right. I think one of the good things about your class is that your class is smaller than the other class, which are given in delivered in Mandarin, right? In that class, I probably have near almost 100 students. And here, I think the number of students is no more than 30. So you have a smaller class. And hopefully, the smaller the class, the closer you are, okay? The more intimate you are. So you can interact with one another to discuss what you have learned or what kind of difficulties you are facing in this class. And hopefully, you will be better connected, not just in this course, but also in the remaining courses, okay? Because this kind of connections, that is the connection you make when you are a college students really matter a lot in the remaining part of your life, okay? Your classmates can become your very good friends and in the future, and they can be very, very helpful for your career and vice versa. You can also be very helpful, beneficial for their careers, okay? So try to learn how to help one another, okay? Make each other better, okay? And hopefully that will make your life more meaningful, all right? Okay, and I believe that matters a lot for all of us. Now, okay, now let's look at simple examples of a spring mass system, okay? And its response patterns is what we call simple harmonic motion. Now, this is the second order equation that can describe a spring mass system. Here, the system has a natural frequency of 8, all right? And it can be shown in the course of engineering mathematics. We were told that its solution can be represented as a linear combination of sine and cosine, where omega here is, of course, the natural frequency of the system. Now, assuming these are my initial conditions, initial velocity, initial displacement and initial velocities. Now, by imposing these two conditions to this representation, it can be easily shown that the value of C1 is 2/3, and the value of C2 is -1/6, okay? Now, next, what I want to show you is that using this representation to represent simple harmonic motion is mathematically valid, but is not that meaningful. We want to represent simple harmonic motion in a more physically meaningful way, okay? So let's play with math. Let's assume the displacement of a simple harmonic motion can be represented as this equality, all right? Now, let's consider this right triangle, okay? Here, the degree, the degree of this angle is 90 degrees, all right? So let's assume the length of this side is C2 and length of this side is C1. And of course, the length of this side is C1 plus, C1 squared plus C2 squared. And then we take the square root, all right? Now, based on the definition of sine phi, let's assume that this is equal to A, all right? Therefore, based on the definition of sine phi from this right triangle, we know that sine phi can be defined, can be written as C1 over A, right? Similarly, cosine phi from this right triangle is C2 over A, right? Okay. Now, let's rewrite this representation as this. We multiply everything by A, and then we divide everything by A. Noting that the reason we want to do this is C1 over A is actually sine phi. Similarly, C2 over A is actually cosine phi. Therefore, what I have for the left-hand side of this equality is A sine phi cosine omega t plus cosine phi sine omega t, right? And for this part, it is actually sine omega t plus phi, okay? So that is the reason why we can rewrite this equality as this, all right? Okay, so what do I want to do that? Okay, because by doing that, we can represent simple harmonic motions, and by using a more meaningful way of representation. Why do I say that? Because if we look at this representation, it actually has three important parameters. One is amplitude, all right? You know the amplitude of the motion. The other is, of course, frequency. You know how fast or how slow the acceleration is. And the third, the phase of the harmonic motion, okay? It can move like this, or it can have the same waveform, but move like this. That is, by changing the phase, you can actually shape, actually shift this waveform leftward in a positive or in a negative direction. You can move it around, okay? Horizontally by changing the phase, all right? So a simple harmonic motion actually consists of three elements: amplitude, frequency, and phase, okay? Amplitude, phase, and natural frequency, all right? Now, so with such a representation, everything becomes meaningful, okay? Because these three parameters directly interpret or directly characterize the moving patterns of the simple harmonic motion. This determines the size. This determines the speed. This, in a way, determines its location in the time domain, okay? Because it can shift forward or backward. All right, and this phase, of course, can be determined from this equality. That is, from this right triangle, you know that tangent phi is actually the ratio of C1 over C2, all right? Now, let's is for simple harmonic motion. Now, in the case of simple harmonic motion, there is no external force because all we have, the reason why it has motion is because initial condition. So simple harmonic motion in essence is actually zero input response or spring mass system, right? It's actually zero input response or spring mass system because the input here is zero, okay? No input has been applied to the system. Now, we want to study force acceleration. That is, we want to apply a sinusoidal input to the spring mass system, okay? The magnitude of that side, amplitude of that sign, so sinusoidal input is F0, and the frequency of the sinusoidal input is gamma. To simplify the problem, we assume their initial conditions. Therefore, here we are looking at zero state response, okay? Now, let's start the problem by using the classical methods, all right? That is, let's assume particular solution to be this form, okay? Why can I do that? This is based on the method that we reviewed last week, which is the method of undetermined coefficients, right? Remember, I gave you that table of method of undetermined coefficients. If this is the Gaussian function, then based on the method of undetermined coefficients, I should assume my particular solution to be this form, that is, to be a linear combination of sine and cosine with amplitudes weighted to be determined, okay? How do I determine the values of A and B? Simple. First, obtain xp dot by taking the derivative of this representation. And then, based on the result, take another derivative, okay? And then substituting the resulting single and double derivatives of xp back to this differential equation. And this is what I will get. And if the method of undetermined coefficient is correct, then this should be equal to this. And this will happen only if F0 is equal to F0 is equal to B times the difference of omega squared and gamma squared, and A has to be zeros, because here on the right-hand side of the equality, there is no cosine gamma t. Therefore, the coefficient of cosine gamma t here has to be zero, all right? So after determining B, we know that the particular solution looks something like this, all right? Now, after applying the given initial condition to the general solution, remember that here we have zero initial displacement and zero initial velocity. And with those initial conditions, it can be shown that this is what I will get, all right? This is what I will get when gamma is not equal to omega, all right? Now, here, what we want to do is we want to study the one particular situation, that is when gamma approach omega, or simply gamma becomes omega. That is, we want to know what happened if the frequency of the input sinusoid is actually identical to the natural frequency of the spring mass system. We want to know what will happen, okay? So to do that, we will run into one problem. That is, if gamma approaches omega, then the denominator here will become zeros. Then this result will become undetermined, because you don't know what will happen if this term is divided by zero. So we rely on the L'Hopital rules, which tell you that if f of x over dg of x has an indeterminate form when x approaches a. You can always resolve this problem by using this rule. And to do that, all you need to do is take the derivative of the numerator and denominator at the same time and find the ratio of these two derivatives. All right? Okay. I'm pretty confident you should have learned this rule before. At least I think it is in the course of calculus. All right? Now let's do that. Okay? Take the derivative of the numerator and let's take the derivative of the denominator. And let's go through after going through all the necessary algebra. I won't go through those algebra one step by step. You go through the algebra by yourself, okay? But even you don't go through the algebra by yourself, I think it is still okay. But the reason why I want to mention this particular mathematical techniques is I don't want you to know this result as a black box result. You don't know what's happening. I just give you a result, and I don't tell you. I never give you the reason why this result is true and where does that result come from. All right. Now we have systematically demonstrated how to get this particular result. Now the next thing we want to do is to find out what does this result mean. That is, we want to interpret this result, okay? Now, in Taiwan, your previous training process is teach you how to find the solution. If you got a solution right, you get a score, you get good grade. But that's not exactly what happened in real life. In real life, getting the right solution is only the first step. After finding the solution, you have to know what the solution really stands for. Okay, how do you interpret this result? Why do we have such a result? What is the physical meaning of this result? How can I use that physical meaning for my applications? Okay, now to understand what will happen, we simply plot it as a function of time, and this is what will happen. And by looking into its elements, the first thing we identified is that here we have a t, which means when t goes to infinity, this thing will goes to infinity. Okay, it will blow up, it will diverge. Okay, and this case of omega approach, gamma approach omega is what we call resonance. The natural frequency omega n is the frequency at which the system would oscillate if there was no driving or damping forces. It characterizes the system's inherent dynamics. So natural frequency is always a property of inherent dynamics. It's the reason why it is called a natural frequency, because it comes from the nature of the system. It has nothing to do with the output. It is the very nature of the system, okay? Because it is the nature of the system, therefore the system, when unexcited by external force, when it moves in the frequency of natural frequency. And resonance, when a system is driven at its natural frequencies, resonance occurs, and potentially it leads to large amplitude of oscillation, right? And why is that undesirable? Okay. Now, before answering that question, let's figure out why this is happening. What is the physical reason the response of system will become larger and larger without any bound? there got to be a reason behind it, right? This does not come from nowhere, okay? This is not an accident. It is bound to happen if my excitation frequency coincide with the natural frequency of the system. But why? The reason is very simple. At the natural frequency, the driving force and the system motion are in phase, meaning the force is applied and synchronized with system acceleration, which means, let's say it's the system move up and down with a natural frequency, okay? If the frequency of the input sinusoidal signals is different from the natural frequency of the system, then they will not move in synchronization, which means sometimes they will move in the same direction, but other times they will move in opposite direction. When they are in phase in the same direction, then the motion of the mass will be enhanced. By contrast, if the motion of the mass is moving in the opposite direction as the direction of the input force, okay, that is, they are moving out of phase, then the force will attenuate the motion of the mass. However, when resonance happens, these two frequencies are identical, and they are always moving in the same direction. Okay, if the external force is moving always synchronized with the movement of the mass, therefore it will always accelerate the mass, try to enhance the amplitude of the mass, make the amplitude of the mass, make the amplitude of the movement of the mass become stronger and stronger, larger and larger, and finally go without any bound, okay? So the reason why resonance happens is the driving force and the system motion are in phase, and this results in maximum energy transfer from the external force to the system, and eventually lead to this kind of disaster situation, okay? You can go to the YouTube and you find videos that voice generate of sound generated by a speaker can shatter, can make a glass break immediately due to the phenomenon of resonance, okay? Now, let's again focus on second order system, but let's now move one step further, okay, to spring mass damper systems, okay? Now, this is a spring mass damper system, okay? Let's replace this B by C, okay? And C here, okay, is actually what we call damping coefficients. And K is, of course, spring constant, all right? And we have shown you that the equation of motion for this spring mass damper system is this second order differential equations. And Y0 represents its initial displacement, and V0, by contrast, denotes the initial velocity of this mass, okay? So let's transform this equation of motion into the X domain. So what we will do is take a Laplace transform of this system by assuming their initial condition, that is, assuming Y0 is 0 and V0 is also 0. Then this is what I will get, okay? Again, we convert this differential equation into a simple algebra equation. Since the goal of control is to plan a set of right input and apply it to the system so that I can get the output to conform to my requirement. Therefore, we care about transfer function, which is defined as the ratio of the Laplace transform of the output to the ratio to the Laplace transform of the input. Okay, and from this equality, we know that the transfer function for this so-called spring mass damper system is actually this. All right, 1 over mx squared CSK. M again is the mass, C is the damping ratio, damping coefficient, and K is the spring constant. No big deal. Now let's define two important parameters. The first is something we already discussed, the natural frequency, which is defined as the square root of K over M. I already told you why larger K resulting in larger omega N, larger natural frequency, why smaller mass result in higher natural frequency. We talk about that. So the physical connection between spring constant and mass, between spring constant and natural frequency, as well as the physical connection between mass and natural frequency should be clear. Okay, now the second parameters, this is the very first time we see it, is what we call damping ratio. Okay, remember there are two damping parameters. One is damping coefficients. Okay, the other is damping ratio. Okay, what is damping coefficients? Damping coefficient is actually a proportionality constant. Okay, it represents the amount of damping force that will appear with a unit velocity. Okay, with a unit velocity. Okay, now damping ratio, okay, is defined by this equality. Okay, now the damping ratio, of course, characterizes the amount of damping effect of the system, of the spring mass system. But why does this representation make sense? First, epsilon is proportional to damping coefficients. Okay, that makes sense. Okay, because if C is larger, of course, the damping effect of the system should be more intense. Okay, but why is damping ratio inverse proportional to M and omega N? To understand that, let's rewrite this representation. Okay, this can be rewritten as C over 2M. Remember that omega N is actually K over M, right? It is written here, all right? So if this is the case, then my damping ratio is actually 2 divided by 2, C divided by 2, and then divided by M, the square root of the product of M and K, right? So damping ratio is actually inversely proportional to the, square root of inertia and spring constant. Why is that the case? Remember that when developing the equation of motion for the spring mass damper systems, we have a free body diagram, right? And the free body diagram shows you that there are several external forces. One is external forces, the force we apply to the system. The other is spring constant. And the other is what? Is damping force, okay? And mx double dot is equal to f minus kx minus cx. All right? So if this is the case, okay, the damping ratio, what you want to characterize is the damping effect. Now, in absolute terms, is of course, this is the damping force, right? But how large the damping effect really is for this system depending on two other factors. The first factor is K. If K is very large, then you have a large spring force. If K is so large, so that Kx, that is spring force, overwhelm the damping force. Let's say it is 1,000 times larger than this force because K is simply significantly larger than C. Then damping effect become negligible. So the impact of damping force really depends on how large spring force is. If you have a very stiff system, you have a very large spring constant, spring force will overwhelm, suppress, will make the damping force look negligible. It looks very, very small. And same thing happened to mass. What we have here is summation F is equal to mx double dot, right? So inertial force is actually the product of the mass and the acceleration, okay? And as a part of the external force, the damping force will have a very small impact on the acceleration if m is very, very large. Let's say m is considerably larger than c. Then the inertial force, then these inertial terms will be much larger than the damping force and even make the damping force look small, appear to be negligible. So how large a damping effect is really depends on three factors. One, how large the damping coefficient is. This represents the damping force, the impact of the damping force in the absolute terms. But you have to compare things in the relative terms, okay? If I'm larger, but you are much larger than me, then in essence, I'm actually small, right? Okay, so this is the reason why we have the square root of m and k here on the denominator of the definition of damping ratio, all right? Because large M means large initial force, large K means large spring force. The larger the inertial force, the larger the spring force is, the impacts of the damping force becomes less and less meaningful, okay? All right, so that is why this definition of damping ratio makes sense, okay? All right, I'm sorry, okay. Another reason why we want to introduce this term is, keep in mind, okay, omega n and eta represents two and only two most important parameters for second-order systems. For first-order systems, the most important parameter is time constant, because time constant directly specifies the pole location. And for first-order system, there is only one pole, okay? So pretty much, you know the time constant of first-order systems, you know the dynamic behavior of a first-order system. End of story. For second-order system, apparently you need to consider more, okay? first order system, 1 parameter. Second order systems, of course, 2 parameters because you have 2 modes because you have 2 poles. And these, which 2 parameters are most meaningful? When I say meaningful, I mean physically meaningful. And the answer is natural frequency and eta. Okay, as you will see in the future that omega n is close related to the speed of response of the system, and eta, by contrast, is close related to the stability of the system. Okay, and these two are 2 of the probably most important aspects for a control system. Okay, speed and stability. So 2 key parameters of second order systems. One is natural frequency and the other is damping ratio. Now, don't confuse damping ratio with damping coefficients. Okay, they are of course proportional to one another, but they are not the same thing. This is damping coefficient. This is damping ratio. All right. Now, here, let's study the spring mass damper system in the H domain. Okay. So what we need to do is we take the full Laplace solution, including initial conditions. So let's take the Laplace transforms of the second order differential equation of the spring mass damper system. And this time we include initial conditions. That is, we no longer assume y0 and v0 to be zeros. I need this. All right. Let's rearrange in terms. Anything related to y is put on the left-hand side of this equality, and the remaining terms are all shifted to the right-hand side of this equality, okay? And this is what we'll get. Now, to solve for y, we'll see that this is what we will get. Again, this is the z-state response, and this, as you can see, are all related from initial conditions, and therefore is, of course, the zero input response. All right? Okay. And for the zero state response, we already know that by taking the inverse Laplace transform of the product of h of x, this is what we'll get, which is the convolution integral of the impulse response and the input. All right? And for this impulse response of this system, okay, that is, if we take the inverse Laplace transform, that is, if we take the, which is mx squared cx over k, 1 over m squared plus cs plus k. We saw that before. Here, if I take the inverse Laplace transform, what will I get? The answer is that I will, of course, get the impulse response. But the mathematical representation of the impulse response really depends on the value of eta. Okay? It can be divided into 3 cases: undamped, critically damped, and overdamped. Okay? If eta, the value of eta is larger than 0, remember that the value of eta is always positive. It cannot be negative. Why is that the case? Because this is the definition of eta. C cannot be negative. It is the damping coefficient of a real-world damper. It cannot be negative. M cannot be negative because it represents the mass. There is no such a thing as negative mass. And natural frequency is also positive because negative frequency doesn't make any sense, because frequency is the number of periods per second by definition. What do you mean I have -3 periods per second. There is simply no such a thing. If Cm omega n can only be positive numbers, of course, eta has to be a positive numbers. Okay, it's not a mathematical result. It's simply physics. All right. So eta has always been larger than 0. Okay, and depends on the value of eta. The impulse response can be represented in 3 different ways. Why is this the case? Let's go back to the course of engineering mathematics. Now, in the course of engineering mathematics, we have to deal with such a so-called homogeneous linear ordinary differential equation with constant coefficients. In the course of control, this differential equation represents a second-order linear time invariant system, right? Now, in the course of engineering mathematics, how do we solve such a differential equations? Again, we make the assumption y is equal to e to lambda x, and we take the first and second order derivative of such a representation, and we substitute them back to this differential equation, and this is what I will get. And for this equality to be true, this polynomial, which is the characteristic equation of this system, okay, is actually this. And the reason why here in discussing impulse response, we have to divide the possible solution into 3 cases is because here we need to do the same thing. We know that the roots of these characteristic equations can be represented by lambda 1 and lambda 2. And based on whether or not the thing inside the square root is positive, negative, or zeros, the nature of these eigenvalues can be classified into 3 different cases. Case 1, I have 2 real roots. This will happen when a squared minus 4b is positive, right? So I have 2 distinct real roots. That's case 1. Case 2 is I have a real double roots. This will happen when a squared minus 4b is 0. Therefore, both lambda 1 and lambda 2 become minus a over 2. So I have a pair of repeated roots. And case 3 occurs when a squared minus 4b is smaller than 0. Then what I have here is a complex conjugate roots, right? Because what I have here is an imaginary number, all right? So I have 3 different cases. Now, for case 1, when I have 2 distinct real roots, then the solution becomes this, right? Pure and simple, 2 modes. What I have is the linear combination of these 2 modes. However, if I have real double roots, this is what I will get, okay? Just think of x as t, all right? Anyway, it is mathematical simple, which is used to represent the independent variable. Now, for engineering analysis, more often than not, the independent variable of interest is time, but it doesn't have to be time, all right? It can also be spatial variable, okay? But when we deal with control system, the independent variable is time, okay? Now, if I have complex roots, that is, my roots look like this, then my solution look like this. Note that the envelope, okay, of this solution actually depends on the real part of the eigenvalues, okay? And the imaginary part of my complex root actually determine the oscillation frequency. of this sinusoid part of my solution, okay? So we learned it before, and this table actually summarizes what we just presented, okay? 3 cases. Now this means roots, and this means actually modes. And this is the general solution, okay? So the reason, here we have 3 general solutions. Therefore, for impulse response, we also have 3 general solutions. And this ADAS, whether it's larger than 1 or smaller than 1, really correspond to these 3 different cases, all right? It depends on it can be shown that this happened, I will show that later, okay? I will show that later. But you know that the thing I want to show you that is to tell you that why there are 3 cases of different types of impulse response. Now, same thing happened to their input response. We also have 3 cases depending on if I have a pair of complex conjugate poles, or a pair of distinct poles, or a pair of repeated poles. Okay. Now, for the second order system, let's first look at the most complex response, which is zero input response that correlates to K3. I think that's enough, okay, for today's lecture. Okay, everything we teach today will be covered in the next midterm, okay? All right, so prepare for it. So please study what you have learned up to now to prepare for the midterm, okay? Okay, today's materials will be a part of the midterm exams, all right? Okay, any question about the midterm exam, please ask now. Okay, don't come to see me. Ask about the midterm exam later. Please, please, please. All right? Okay, so I'll see you next Wednesday. Okay, I'll see you next Wednesday. Oh, by the way, we have another holiday coming this weekend. Have a wonderful national holiday. OK， 好，谢谢，东西就交给你了哈，麻烦，给你开溜了。